Another short lesson from me today. Today, I'll just like to tell you about one of the great experiments of nuclear physics and try and explain how it was carried out. That experiment was called the Rutherford Experiment. It was carried out in 1911 in Manchester University in England. The person that came up with the experiment was Sir Ernest Rutherford. He wasn't a sir at the time. He didn't actually carry out the work. His research students carried out the work. Um, and what they discovered really was the modern model of what we think an atom is like. Basically, that we have electrons around a very small positive nucleus. The experiment is actually very, very simple. Um, but Rutherford didn't win his Nobel Prize for that experiment. He'd won it earlier in 1908, and in one of the great ironies of science, he won it for chemistry because at the time the Nobel Prize Committee didn't really recognise the idea that nuclear physics was part of physics. It didn't really exist as a subject. The irony is that Rutherford, he always said that there was no real science other than physics. That's why he studied it, and he won his Nobel Prize for chemistry. Okay, so if I show you the people involved, this is Rutherford. There's one of his famous quotes about the other sciences. He was born in 1871 in New Zealand to a very poor family, very large family. He had 11 brothers and sisters. His dad was a flax miller, so that's somebody that collects seeds from the flax plant, makes them into threads, and then makes them into linen cloth. So it was a poor family, but his mother was a school teacher, and she was the person that really got him involved in science. On the other hand, these are his two students that worked with him at Manchester. This is Hans Geiger. He was born to a much wealthier family in Germany. His father was a professor. During the First World War, he left to join the German military, and he served in the German military. And in the Second World War, he actually worked on the German attempt to create an atom bomb, which wasn't successful. Marsden was born in England. He lived longer than the others. Rutherford died in 1937. Marsden, I think, died in the 1950s. And Marsden actually worked on the Manhattan Project, which was the successful Allied project that created an atom bomb. It's quite sad that Rutherford, he died just before the war, but one of his great fears was that his work would be used to create an atom bomb. And that's exactly what happened with one of his own students. So if I go back a little bit in time, in 1895, at the age of 24, Rutherford came to Cambridge University in England to work with this guy, Professor J.J. Thomson. He was so smart, he got his physics degree in 1 year at Rutherford. Thomson at that time was one of the most famous physicists in the world, and he'd just discovered the electron. And in doing that, he created one of the first accepted models of what an atom is like. So basically, he knew that electrons were small particles. He knew they were scattered around he thought they were scattered around the atom, and he thought the rest of the atom was positive charge, because they knew that there was positive and negative charge inside an atom. So this was his model. It's kind of jokingly referred to as the plum pudding model, after the English dessert, where the electrons are scattered around like fruit inside a pudding. So at the time, scientists thought that the atom was like a billiard ball, positive, as is shown in blue, with these negative electrons scattered around like plums in a plum pudding. So the work that Rutherford and Geiger and Marsden did, which we should refer to as the Rutherford-Geiger-Marsden experiment, was to prove that was wrong. And what they proved was there's a nucleus, central nucleus, and the atoms are scattered around the outside of the nucleus. You already know that model. You've already seen that lower down the school. So Rutherford proved his old professor to be wrong about the model of the atom. So to finish this, I'll just show you the apparatus they used and how the experiment actually worked. So I hope this is visible on your screen. I'll try to explain it as best as I can. It's a fairly simple experiment, actually. So the first thing that Rutherford got Geiger and Marsden to create was this thing, which we could call an alpha particle gun. It's an alpha particle source. I'm not sure exactly what element they used actually, but it was something that produced alpha particles. It was put in a lead box, and there was a hole in the front of the lead box, so the alpha particles could only go in one direction, forwards. They created a vacuum chamber. The whole thing was inside a vacuum chamber, so there was no air particles for this beam of alpha particles to bump into. In the center of the chamber, they put a very thin piece of gold metal or gold foil. So thin, in fact, that it was very close to being just one atom thick. I'm not sure how they managed to do that, but apparently they did. And the experiment was so simple, it was just basically firing these alpha particles at the gold foil, and they wanted to see what the gold foil did to the alpha particles. If Thomson's plum pudding model was correct, then you'd expect basically all of the particles to just bounce back off the foil because they just hit the positive charge. Rutherford knew that the alpha particle was positive. So we have the alpha source, we have the foil, and around the outside of the foil you've got, in its basic form, it's kind of a screen. It was a very early type of Geiger counter, which Geiger put his name to, although he worked on it with Marsden, the Geiger-Marsden counter, which is a radioactivity detector. It's basically just a chemical screen, and when a particle, a charged particle hits it, you get a little flash of light. So basically, Geiger and Marsden spent months sitting around this screen, just counting flashes of light on the screen and making a note of where the flashes actually happened. So as I said, if the plum pudding model was correct, the particles would bounce back. That's not really what happened. So three things actually happened. So I've put those three things at the bottom here, which you can see. Okay. So three things happened. Number one, most of the alpha particles hit the gold foil and went straight through and hit the back of the screen. So that reflects conclusion number one up here. Number one, most of the atom was therefore empty space, so the alpha particles could just shoot straight through that empty space. That was a great discovery on its own. But then, number two, they couldn't really understand it at first, but what they found was a small number of particles actually bounced straight back. Now that was completely unexpected. If most of the particles went through, something was in the atom that occasionally the alpha particle hit and caused it to bounce back. So what they discovered was there was positive charge inside the atom, but it was very dense and contained in a very small space. So what they discovered was the nucleus. They discovered the nucleus of the atom. They hadn't named them protons at that stage, but they discovered the proton inside the nucleus. So that's number two. And then number three, as you can see here, a very small number of particles hit the foil and they didn't go straight through. They were deflected in one direction or the other direction. So what that means was when some of the alpha particles came close to this nucleus that they already thought might exist, it was deflected off in one direction or the other direction. It just kind of came close, but was deflected because positive charge repels positive charge. So they also discovered that the nucleus is not only small, they discovered it was very small and positive. Yeah. Basically, the sizes of the nucleus, that it was so tiny, was given to them by the number of particles, the ratio of particles that went through, the ratio that came back, compared to the ratio of the ones that were deflected slightly. Okay, so that's the Rutherford Geiger Marsden experiment with the conclusions above my head. Hope it made sense. I'm just going to upload this for you with a few questions that I'd like to answer to see if you can test your understanding. I'll also give you a link to a YouTube clip that actually shows you a real physicist carrying out the experiment in a modern day setting, so you can see actually how it was done, much more professionally than my little video here. Okay, any questions as usual, please get back to me. I'd also like your feedback on these video lessons to see if you think that they're working and if you want to continue with me trying to churn these out on small topics like this. Okay, thanks for your attention. Stay safe as usual. And as I always say, hopefully see you in a few weeks. We don't know when that's going to be. Look after yourselves and your family. Okay, goodbye.